let's do some examples. Okay. So example 1, we know that the Laplace transform of 1 is 1 over s, and it only holds for s greater than 0. So if we wanted to do this as using the exponential order, right? So we used it as, okay, we did this once by calculating the Laplace transform. We can also do it by doing the exponential order. Why? Well, absolute value of 1 is equal to 1. And I already explained how this is always less than or equal to t, for t greater than or equal to 0. And in fact, you can show that this is true, right? So this is true for t greater than or equal to 0, and for in this case, a equals 1. But in fact, this is true. So in fact, it is true that the absolute value of 1 is equal to 1. It's less than or equal to e to the at, as long as a is greater than 0. Right? How can you think of this? Well, e to the at, if a is greater than 0, that's a growing function, right? It's a function that's increasing. Right? At 0, it's 1. So for any value, so for a equals 0, it's 1. For any value a greater than 0, then it has to be bigger. It has to be a higher value. So that tells you that this is true. So this implies f of t equals 1 is of exponential order. Right, it's of exponential order. So we can find what the constants are with. Right, so m here is 0, right? So it works for all t greater than or equal to 0. So m is 0. K is 1, and a is just any number greater than 0. Moreover, 1 is a constant function, so it's continuous. And again, anytime your function is continuous, by definition, it's already piecewise continuous. So, and since 1 is continuous, it is piecewise continuous. Right? So we know that L, which implies that we know that the Laplace transform of 1 exists for all s greater than a, and a here greater than 0. So same as saying s greater than 0. Right? So that's another way of, actually let me do that, for s greater than a greater than 0, which means s greater than 0. Okay? So this is how you would use theorem 2. Right? So I showed that it's of exponential order, and then I argued, it's continuous, so it's piecewise continuous. Most assumptions of theorem 2 are satisfied, so we know that the Laplace transform exists without actually having to compute it. We can do something similar for the other one, for the Laplace transform of e to the at. Right. So here, I gave you what it was, it's from the theorem. Let's actually use exponential order. Right. Well, let's look at f of t equal to e to the at. Well, this is obviously of exponential order, right? Because we can say, okay, the absolute value of let's say of e to the at, as long as a is greater than 0, right? This is going to be above the x-axis. This is just going to be itself, again, for a greater than 0, which is less than or equal to itself, right? Everything is less than or equal to itself, right? So here, what do we have? We have what are our constants? This implies. So this works for all t. So we can take m to be equal to 0. So this is saying that this works for all t greater than or equal to m, which is 0. Right? A is just a, right? But let me just say that we're assuming that it's greater than 0. And k is 1. So this function is of exponential order. We know it's continuous. Right? And the result follows, which implies the Laplace transform of e to the at exists for all, in this particular case, s greater than a greater than 0. Right? So here is more, it's more, so I wrote the same thing, but it's more restrictive. So actually, let me not use greater than 0. Because for the Laplace transform of 1, it doesn't matter what a is. Right? Because it's also true for a equal to 0. Right? So as long as s is greater than 0, this holds. In this case, it does matter what a is. If, for example, our function is e to the 3t, then the domain of the Laplace transform is going to be s greater than 3, not s, which is greater than 0. Right? But you don't get everything, because if s is greater than 3, it is true it's greater than 0, but everything between 0 and 3 is not actually included in the domain. So let me write that here as an example. So for example, if f of t equals e to the 3t, then the Laplace transform of e to the 3t is going to be equal to, let's look at the formula, 1 over s minus 3 for s greater than 3. So noting that this means this doesn't hold, or the domain of this function is not anything less than 3 or between 0. Right? So meaning the domain of this Laplace transform is the interval 3 to infinity. So it's not defined for anything less than 3. Again, in practice, this is not going to matter too much. Right? We won't be too interested in the domain, but it's important for us theoretically, because remember that all this comes from exponential order, and that's how we show that a function has a Laplace transform. We can either calculate it explicitly, or you have to show that it's piecewise continuous and of exponential order. And it's not for all a's that a function is of exponential order. Right, so it matters that this works for s greater than a in this example. So again, when you're doing things with exponential order, you can see the domain showing up again. So again, in this case, s has to be greater than a. In the Laplace transform of 1, s has to be greater than 0. Again, in practice, we won't be working too much with this. But theoretically, especially when you're working with functions that arise in your system, so you're modeling, for which it is not known whether the Laplace transform exists, you're going to have to do some analysis like this. And all of this is important. Theorem 2 is very crucial for that, if you cannot compute the Laplace transform directly. Okay, so here's an example of using this theorem 2.